Good morning all. Continuing from the last video, today we will discuss about the characteristics of JFET. So the JFET characteristics curves, in first case we have to take that VGS or the gate to supply voltage is 0, whereas VDS is supplied and VDD is supplied. So with increasing VDD, when VDS is increasing, ID increases. This ID increases, therefore ID is proportional to VDS for small value of VDS. Now if we increase the VDS value uh, in extremely at larger value of VDS, the depletion layer becomes wider and causing the resistance of channel increases. So gradually it stops the conducting. Then at VDS equal to VP, which is called as pinch off voltage that we have already discussed in previous class, is reached, the ID becomes nearly constant and IDSS drain to source current with gate saturation. Now this is the characteristics curve for JFET, where we can see the x-axis is VDS and y-axis is ID. Starting from 0, it is increasing gradually. When it is increasing, the VDS is increasing gradually till VP value, till this VP value or pinch off voltage value. When VDS becomes equal to VP, the IDSS or the saturation drain current starts to conduct and the characteristics curves settled over there and go to saturation level, and this happens in VGS equal to 0. So we have not applied any gate to source voltage or gate voltage till now. Now here N channel JFET characteristics curve with IDSS 8 milliampere. This is a example where we can see at different VGS. Now with VGS 0, so the lower one, the lower curve we are seeing over here is with VGS 0. So we have not applied any negative gate voltage across gate and source or within between gate and source terminal. Now if we place or if we do not shift or do not increase the VDS value at first instant, so first we will, what we will do, we will increase the VGS value by some value. Here it is taken as per the graph, it is taken as -2 volt, and we will put that VGS value same, or means VGS value fixed over here, and we will now increase the VDS or VDD to see the characteristics curves for JFET at VGS equal to -2, where we can see the IDSS now is has increased and the value is higher than the value where VDS is 0, VGS is 0. So in that case, when we will again increase the negative voltage VGS equal to -1 volt, so -2 to -1 volt, so we are increasing the negative gate voltage. So in that case, we can see again the saturation point or the pinch off point has increased. So and the value of current or saturation current has increased with increase of VGS value. So not only on the VDS or VDD value, it is the saturation, the IDSS or the saturation current value, drain current value, is also dependent upon this VGS value. Then at VGS equal to 0, at VGS equal to 0, we can see the IDSS has increased again and the value is saturated over here. Now in these characteristics we can see 3 points. One is ohmic region, and in between it is the pinch off point, and the right side is the saturation region where the current doesn't change with respect to the voltage increase. So current value through the JFET is being fixed. So this is, that's why it is called saturation region. Whereas in ohmic region, with increase of uh, voltage or VDS, the current value increasing gradually. Now this is the same thing just that we have seen in case of P channel. Now we can see in case of P channel the VGS need to be present at is positive gate voltage. That means the plus terminal of the battery will be connected to the gate terminal and minus terminal of the battery will be connected to source source terminal. Okay, so in that case we can see in case of VGS 0, in case of VGS 0, that 0 volt means there is no gate to source voltage. The pinch off value is somewhere here where the current is going from ohmic region to saturation region. Similarly, with increase of positive gate voltage, we can see for plus 1 volt or plus 2 volt and plus 3 volt plus 4 volt up to plus 5 volt. It has been shown 5 volt of gate to source voltage. So with increasing positive gate voltage, the current value is gradually decreasing. Moving on. So this is the again characteristics for n-channel JFET, where we can see the if VGS is 0, the IDSS value is higher, and if the negative gate voltage increases, the IDSS value gradually decreases uh, from higher value to lower value. Operation of n-channel JFET. Now JFET is biased with two voltage sources. So as we have seen that two voltage sources is needed to properly bias a n-channel JFET. One is VDD, another is VGG. VDD is drain to VDD is responsible for providing voltage to drain to source voltage, and VGG is the gate voltage which is responsible for providing gate to source voltage. Here we can see it is written VDD generate voltage bias between drain and source, and VDS that I have said already, and VGG is generate voltage bias between gate and source, which is basically the VGS. So in case of n-channel JFET, we apply negative VGS, and in case of p-channel JFET, we apply positive VGS. Now we are moving on to characteristics curve. So this is the characteristic equation of any JFET. So here IC equal to beta into IB. IC is collector current, whereas beta is the base current. But this is for BJT, not for JFET. Here beta is the gain of the BJT. This is given, or this is written over here uh, to match or to show the inner relationship between these type of devices. Now, as we have seen the characteristic equation of BJT in the previous slide, this is the characteristic equation for a JFET, where it is written ID equal to IDSS into 1 minus VGS by VP whole square. Now ID is the drain current, we all know, and IDSS is the drain current at saturation. Then it is 1 minus VGS by VP. VGS stands for gate to source voltage, and VP is the gate to source voltage at off condition. So this is VP is basically the pinch off voltage when the switch turns off, and it is also called Shockley's equation. Generally, this type of FET device means JFET, MOSFET, uh, all these type of FET devices follows these characteristics equation. Now this we are seeing over here is the JFET transfer characteristics. Characteristics curve we have already seen in previous slides, how it is drawn or how it is seen, where this portion is ohmic region and this portion is the saturation region, whereas this point is the pinch off point. And with increasing gate voltage from -4 to 0 volt, we can see the value of IDSS is increasing. Now in the left side we are seeing that the transfer characteristics of JFET, where the x-axis, or rather we should say the negative x-axis is VGS and the y-axis is ID. With increasing negative gate voltage, the ID is, or IDSS is increasing. So this is drawn at specific value of VDS, because here there is no option of changing VDS. So for different VDS we have to draw another transfer characteristics for a specific VDS value. When we are increasing the negative gate voltage from -4, -3, -2, -1, like up to 0, the current value is, or the drain current value is increasing gradually. And this equation is basically, this equation is the transfer characteristics equation that we have seen in the previous slide, that is the Shockley's equation. So here is some exercise. Sketch the transfer defined by IDSS equal to 12 milliampere and VGS equal to -6. So for that, again we have to see these equations. VGS equal to Vp into 1 minus root of ID by IDSS, and similarly same, means these two equations are same, that's just two different format. This is in terms of voltage and this is in terms of current. Now as some values are given over here, VGS equal to uh, 0, 0.3 Vp and 0.5 Vp and Vp. ID over here, ID is IDSS, IDSS by 2, IDSS by 4 and 0 milliampere. So VGS here is taken as 0 and 0.3 or 30% of the pinch off voltage, 50% of the pinch off voltage, and at the pinch off value. And respective ID current we can see at 0 VGS we are getting maximum ID current. IDSS at 30% of Vp we are getting half of the IDSS that we got maximum, and at 50% of the Vp we are getting 25% of IDSS, and at pinch off the current conduction stops through the device. And according to that value, here we are drawing the transfer characteristics here, where again we are taking this x-axis or minus x-axis as VGS and ID as y-axis as ID, and at VG is equal to Vp, means at pinch off the voltage has some higher value, VGS has some higher value, where the current is 0, means at pinch off the device is in cutoff region. Then gradually the voltage is increasing at 0.5 of Vp, means 50% of the pinch off voltage. It is achieving 25% of IDSS. At 30% of pinch off voltage, it is achieving the half of the IDSS, and at last at the maximum point we are getting the, when VGS is equal to 0, we are getting the IDSS or the maximum saturation drain current. So this is the total answer of this question.